here at the age of 19, let alone getting a PhD by then. He's been highly praised as a practitioner of different crafts. He's a mathematician, he's a physicist, he had published more than 80 journal articles. He also had another 22 unpublished articles when he worked for the Atomic Energy Commission. And he's the only African-American mathematician engineer who was elected as fellow to the National Academy of Engineering. So certainly it's a great honor of mine to really introduce the speaker that we have here. We'll introduce the person who's going to introduce the speaker. Because I think that our speaker really does embody the genius that is Jarence Wilkins. So before I really get over to the introduction, I actually want to show a quick video, at least a snippet of it, of something that I found on Facebook just a few days ago. So our speaker here was saying that Facebook is going to launch a channel that will compete with YouTube, well, really a video streaming service. And they have a channel here that's called Big Ideas with Little Kids. And the caption here says, "This physicist attempts to teach 7-year-olds string theory." So let me just see if I can show a little bit of the video.
People think scientists are supposed to be really, really smart, but really good scientists are actually really dumb.
What?
Yeah. Hi guys, my name is Stefan.
Hi, Stefan.
I first want to know what you know about string theory.
You can pull it.
Okay.
Theory.
I love all your answers. String theory is a unifying theory, right, that says that all the substance in our world, matter, energy, the stuff that you're made up of, and even space itself, all comes from vibrating strings. So how do you guys think all these forces come from strings?
It makes things stick together, like us sticking to the chair instead of floating off.
Matter is made up of dots, and we call these tiny little dots, right, atoms.
But why can't we see the dots? Because they're inside our molecules.
That's why we're going to do an experiment.
Experiment one.
So notice when you look at this picture with your naked eyes, you have to put it down. We're doing an experiment now.
Sounds like Chinese food.
So, when you look at this picture, you see that the image is smooth, very smooth. But if you take your magnifying glass now and you zoom in, so take your magnifying glass and
Is there
start
a
looking,
lumpy?
you see dots. You see it's actually made up of dots, little tiny dots.
I think that the dots are made of string.
Okay, you're giving away the answer. Stuff is made up of tiny dots when you zoom in to very tiny distances.
I can see dozens and hundreds of little dots.
Exactly. Physicists are still curious. We want to know what the atoms themselves are made up of. And we discover a beautiful idea. And that idea is that even the particles, these atoms, are made up of vibrating strings. There's no magnifying glass that we have today that can actually go to such distances to see strings.
I can see them.
That sounds you're onto a big breakthrough, because that's what we're trying to figure out, how to see strings. So how about we take a snack break?
Yeah! Snack time!
You know, scientists are like kids, because we're always exploring and curious about things. And I want you guys to teach me something.
Elephants can feel a vibration for more than 5 miles away.
I never knew that.
Karate.
Karate.
No.
I don't know karate, and so what are we going to tell me about karate?
I used to have a yellow belt, but I went back to white.
Wait, you got demoted? How did that happen? That sounds like me, like I almost got demoted from 3rd grade to 2nd grade.
3rd grade to 2nd grade. Wait, but that doesn't make sense. You're a scientist.
Really good scientists are actually really dumb.
What?
Yeah.
Because they discover things?
That's right. Sometimes to discover something, you have to kind of forget everything that you know. Would you like me to show you?
Yeah! Experiment 2!
Okay, maybe I'll pause here then. So certainly, take a look at the rest of this video. It's certainly really fascinating, and I definitely am looking forward to the other videos that we have here in this series. So let me then bring up the department chair here, Jean-Michel, who will then introduce our speaker.
Good afternoon. It truly gives me great pleasure to introduce my friend, Stephen Alexander, my classmate. I met Stephen in the 1990s at Brown when I arrived in Providence. We did Thayer Street together. Right? So he was in the physics department and I was in applied mathematics, and trying to figure things out, what we wanted to do, whether we belonged, in that place. Well, everything for me was one step higher, and we were being challenged and about responding to the challenge. We spent a lot of time together. I remember he was always intense, like that, and, right, and always thinking about the universe, cosmology, always trying to explain to me what an M-brain is, and I still don't understand it. M-brain, right? M-brain, B-R-A-N-E. I thought he was talking about the membrane. M-brain, right? And he told me, no, they also have D-brain. Am I correct? I still remember. Yes. And I would, after talking about physics and the stuff I was doing in dynamical systems, we would end up at a pizzeria, and I would be buying, right? And he would be eating because he was hungry for all that thinking, right? And I hope they still have these hearty sandwiches, right? And I think he graduated in 2000, right? And I graduated, and I went to IPAM, the Institute for Pure and Applied Mathematics in Los Angeles. And I was doing a postdoc there. And one day we had a big meeting, and whom did I see coming from far away? It was Stephen again. And he had a retinue of reporters from the LA Times. Remember that? And I said, man, this guy, I can't keep up with him. It was 2003, I think. And the next day, 2 days after, in the Sunday Times, I saw an article where you were cited by that lady about the conference there and his theories. He was always on the cutting edge of things. And as you can see, even his video now, this is part of the Facebook's effort to basically take on YouTube. And not many people know about that initiative. But you can see he's in the middle of it. So it is with pleasure that I present to you Stephen Alexander. And you're going to talk to us about the connection between music and mathematics. So welcome.
Meanwhile, I did bring, I'm a physicist, but I'm a theorist, so I can't do anything with my hand except my experimental apparatus, my soprano saxophone. So I'm just going to take it out, because I will be doing some demonstrations. It's kind of great. I've gotten to a place in life where I can actually use my horn as a prop to do demonstrations. Okay, so it's a real honor, and it truly is an honor. I mean, I told myself this summer that I was not going to do any traveling for reasons that are not interesting to you. But basically, I want to just relax and stay at home. But when Edre contacted me, I couldn't miss this because, Wilkins was such, as a young, African American sort of in the mathematical sciences, you do look around. I mean, you do look around, for example, for people who are like, who's your Einstein, right? And I think, did he published also with, who's the other great physicist that he published? There's a theory named after it. Wigner, that's right. Like one of the architects of quantum mechanics, Wigner, Eugene Wigner. So like, there's a Wilkins-Wigner theory. And so I was very aware of this. And that, having people like that as, flagposts, that you can also realize that I can, wow, that's part of our tradition. Like, we have geniuses too like that, So it's a real honor to have been selected to sort of be a part of this and to honor Dr. Wilkins. So I want to just, obviously I got to do a little bit of advertising here. So a lot of the stuff in this talk today, a lot of the material, is coming from my book, The Jazz of Physics. You can get it anywhere. Amazon is coming out in soft cover next month, so you can get it for like a very cheap price now. Yeah, so that's kind of a little plug to my book, and I promise I won't say anything more about my book after this. All right, let's begin. So my talk begins with a little bit of a narrative, a little bit of a story. All right? As I was growing up, and I grew up in the Bronx, New York, my dad was a cab driver for the first Caribbean cab company in New York City called Skyline. All right, he was car 3. And I grew up in a very musical family. I think, it's safe to say, and all I really mean by that is that I grew up in a household where I would come home and my dad would be playing like, some, I don't know, Barry White, to some Bob Marley, to some Coltrane, right? So I grew up in a family where music was always around me, right? I also grew up with the expectation that I would become a musician. So a professional musician. My grandmother, took her savings so that I could become a concert pianist. So there was this expectation, and that expectation is, of course, coming from the fact that, for Caribbean immigrants, one mode of economic success, right, and it's no different than any of the diaspora, is either entertainment, music, sports, or other more onerous things that, can get you in trouble. So the basic point was, society, and society certainly, the media definitely presents us with, sort of like, in a way that, where there's an abundance of us doing those kind of stuff, and those things are good to do. But as a kid, I was also very inquisitive. And I was always attracted to understanding the why behind the why. And I didn't realize that actually these things, people got paid to do these things. And my first exposure to that was Marvel comic books. So I was a big fan of Iron Man. And I learned that Tony Stark, at age 8, was a physicist, right? And so, so at a very young age, there was this thing where I knew there was this push and this expectation for me to become a musician, but there was this part of me that was attracted to the sciences. And when I looked around, I didn't see any role models as scientists, and I saw far too many that were musicians. So as you see, it was, I had a little bit of a dilemma. And this dilemma lived with me throughout my life, right? So, and that, what was really sourcing that dilemma was, number one, I didn't have role models. We don't have these types of role models out there in the popular media. Okay, it's safe to say now, everybody thinks Neil deGrasse Tyson is, at least he's there, and like, he's the new genius and that kind of stuff. But, when I was younger, no one existed at that level. And therefore, the natural, I think, observation that I made as an 8-year-old kid was maybe we just can't do that kind of stuff. So in other words, the media also presented, like the media would present images, on TV as to what a scientist looked like, So wait, what is my picture? Usually I had a picture of, you know, the stereotypical scientist, you know, an old white guy in a white lab coat, right? That has no personality whatsoever. I mean, people argue I don't have a personality, so let me take away that designation. And you know, when I saw musicians, you know, oh yeah, you know, they all look like me, more or less, right? I had dreadlocks growing up, just so. But something really interesting happened. In the 80s, in the Bronx, as you know, this thing called hip-hop music was pouring out of the streets. I know Brooklyn still wants to try to claim that it came from Brooklyn, okay? But I'm here to stand on Brooklyn ground and say it came from the Bronx before the exile. I know, I should be very careful. Close the door, please. So the high school I went to was called DeWitt Clinton, and turns out the nickname for Clinton was called DeWitt 5%er. Now, I'm not going to talk about who the 5%ers were, but that's, you know. But it turns out a lot of rappers from those days were 5%ers. And probably the most influential one to me was this guy. This is Rakim, considered by many to be the greatest MC of all times, including, I mean, Eminem even said that about him, okay? So the thing about Rakim was that he was, the 5%ers believed in something called supreme mathematics. Right? So their God was math. And they believed in actually, so they would basically drop science. So on the street corner, the improvisational raps that they would have was actually not called rapping, it was called dropping science. Right? So on the street corner, that's what the rappers were doing. So here's an example of like one of the raps that Rakim, my melody, he goes, that's what I'm saying. I drop science like a scientist. My melody's a code the very next episode. Has a mic off in the starting, ready to explode. I keep the mic at Fahrenheit, freeze MCs to make them colder. The listener system is kicking like solar. So the thing that was interesting as a 13-year-old when I'm hearing this, here is the most popular rapper out there that everybody's looking up to, and he is making allusions to scientific concepts. So Rakim became like this role model that made it okay for me to sort of like, hey, like, here's this famous rapper that's interested in the sciences and in mathematics and this kind of stuff. If you listen to many of his raps, like, they get very interesting, right? I mean, he develops a whole cosmology. So that was interesting. And that kind of made me start entertaining this idea at that age that, hey, you know what? Keep doing the music. But it's okay to pursue my passion as a scientist. The other person that was influential was Albert Einstein. And I guess the reason why Einstein was interesting to me as I, you know, started to read more about him as a teenager was that he was just weird. I just got the sense that Albert Einstein was like, that if I were to cross Albert Einstein in the street, right, he would have said hi to me. Well, I of course come to learn later on that Albert Einstein was actually a civil rights activist. He was friends with Paul Robeson for over 20 years. He defended W.B. Du Bois in federal court. In fact, told the judge and that if they mess with him, that they would have to deal with Einstein, okay? Friends with Langston Hughes, okay? And the only place he chose to ever give a talk later on in his life, right, was Lincoln College, a historically black college. There's a picture of him doing that. So again, my intuition was right that Einstein probably was one of these, there was something about him, aside from just his genius and also the fact that he was an ideas-driven type of person. It gave me the sense that, hey, maybe I don't need to be, you know, I can just think about physics. I just had this. I was very naive at that time. All right. And of course, John Coltrane was another big one. In college, in high school rather, and later on as a postdoc, when I listened to Giant Steps the first time, I said, you know what? I said to myself, there's something more than, Coltrane was hip to something else. There was something more to why and how he was able to solo over giant steps. So I had this hunch again, that Coltrane was kind of taking out mathematics on his horn, that there was some geometric principle. I just had this hunch. Then fast forward, like, 15 years later, I'm visiting a friend of mine. When I was at Stanford, I was visiting a friend a sax player, and he had a book written by Yusef Lateef. It's Syllabus of Scales and Melodic Patterns. And the book was daunting. It had thousands or hundreds of scales, no words in it, and one picture at the very beginning. And it was this diagram. This is a hand-drawn diagram by John Coltrane himself that he gave as a birthday present in 1961 to Yusef Lateef. And when I saw this thing, at the time I was working on some crazy idea in quantum gravity, where we were working with certain discrete types of geometry. And I looked at this thing, and I said, my God, there's like so much resemblance to these types of discrete geometry in this. And so I started actually doing some research on this to try to reconstruct maybe what Coltrane may have thought, because he didn't reveal any information to anyone about this. Come to discover that, and I'll talk about this later on, that there was a great composer, Dave Amram, who was the composer for the New York Philharmonic, who was friends with Coltrane, and they used to talk theory a lot together. And Coltrane revealed to him that he was a big fan of Albert Einstein's work, and he studied Einstein's theory of relativity, and he was trying to construct a system similar to Einstein for music. Okay? As we progress later on, I'll actually reveal some information about this diagram, and actually it does have to do with some ideas in differential geometry. Okay, so at some point, my music world and my mathematical physics world really started to mend. So I kind of want to talk about how that happened. Well, first of all, it happened because some crazy Portuguese physicist was mad enough to decide that he wanted to hire me. And that was 17 years ago. This guy came down to Brown University, and I remember the talk. The title of his talk was called Photographing the Wave Function of the Universe. And I was like, this guy's mad. Okay? He wants to take a photo of the wave function of the universe. And then we were talking, we had coffee, and I was showing him a calculation I was working on. And then he hired me to do my first postdoc at Imperial College. And coincidentally, 17 years later, that guy's in the back of the room. João Maguijo. And then what happened when I was in London, I became good friends. Wait, what happened to my picture? So I became good friends with a musician, a composer, by the name of Brian Eno. Does anybody know who this guy is? Yeah. Okay. How many people know the band U2? How many people know the band Coldplay? How many people know David Bowie? Roxy Music. Okay, it goes on and on. So he was the producer of all these individuals. But Brian Eno was a very interesting producer. He invented a form of music called generative music. Okay. And the idea there is that instead of creating a structure of a musical piece first and laying down notes and chords and harmony based on that structure, you start with very simple rules. Think about like a differential equation, and you let that dynamic, okay, generate the complexity and the emergence of new music. And the idea is that every time you run the music, this generator, okay, it will generate completely new music every time. And the idea is that the music would be interesting. So he had an album called Music for Airports. That's an example of generative music. And around that time, I used to go, before going into work at Imperial, I used to stop by and have coffee with Brian in his studio. And one morning, it got to the point where I was showing up so often, he'd just leave the door unlocked. So I just walk in, and he'd be at work with his computer screens. And one day I walked in, and I saw gigantic screens with these types of things on it. And I saw this guy like completely entrenched, like, you know, what's the word? Like engaged with this thing. To the point where even when I walked in and I made a loud noise, he was like uninterrupted by it. I'm like, what the heck is this guy doing? It looked like he was playing like these prehistoric video games. And I thought he was losing it. I'm like, so every day I would come, he'd be working with this stuff. I said, what's this guy doing? Fast forward like, 15 years or so, that stuff turned into this. This was something that he sold to Apple Computer, I believe. I think it was Apple. And it's something like 1,000,001 paintings. Basically, he created something called generative art. What Brian was doing back then was he was playing with cellular automata, okay? Which is this idea that you have these local neighbors and you assign, very simple rule, and you then let this thing go crazy, and you develop beautiful patterns, some more interesting than others, and this is this idea for how evolution might happen. And I know that there's some connections to dynamical systems here. There are connections in physics to black hole thermodynamics, for example, with this stuff. But the point there, and the thing that was important for me to have realized at the time, was that Brian Eno was this world-class artist who was dabbling, right, fearlessly with cutting-edge mathematics. In other words, Brian Eno wasn't saying to himself, oh my God, woe is me, and like I'm so ashamed, to be playing with these ideas in math. Like, what are my colleagues are going to think about me? He just fearlessly would just take ideas and cutting-edge ideas, even though it was missing, he didn't really understand it completely, right? But he would freely, like, there would be this backflow of osmosis of physics and mathematical information. And I noticed that he also loved hanging out with physicists, right? And that's why I was one of his friends. Why? Because he would like, what are you thinking about? Well, I'm thinking about string theory. Okay, tell me about string theory. And he just wouldn't stop. But guess what? You can see the impact it had on his art. And so what that did is it inspired me. Say, if Brian Eno could do that with his art, why should I, close my mind off, my brain off, to how my music might influence? Because at that time, even way into a postdoc, even when I was a graduate student, I really wouldn't mix my music life, and what I meant by that was socially. I wouldn't bring many of the few physics friends that I had to hang out with my music friends. I kept those real separate. And part of why I kept that real separate, I felt like I wouldn't be taken seriously. It's already hard enough as, a black person trying to pursue what we pursued, to be taken seriously by your colleagues. At least that's how I felt. And, if I then reveal that, like, I'm a softie, or I'm trying to be a rock star, what have you, by maybe their perceptions, right? Then I definitely wouldn't be taken seriously. So there was definitely that kind of hyper-awareness where I deliberately kept those worlds not talking to each other. But Brian Eno inspired me to say, you know what? Screw it. I'm just going to go for mine. Now, I'm exaggerating a little bit. I mean, I did have friends like Joao and, other science friends who were always encouraging me to say, hey, next time you have a show, invite us all, that kind of stuff. But, so I want to now talk about the connections that I discovered over those years. Now, obviously, I wrote a 300-page book that goes into much more detail. I only have, 40-something minutes to kind of gloss over some of these ideas. But what I hope to do is to actually show you some mathematics and some ideas in physics that you're kind of already familiar with, right? And shed some musical light on it, so that the ideas that might deepen and enrich your understanding of the physics and the mathematics, right? So that's kind of what I hope to do in the next slide. The first thing I want to talk about, I want to kind of develop a language so that I can use this language to kind of talk about music and physics and cosmology and all this stuff, right? I want to talk about the idea of the superpositions of periodic waves. So consider a periodic wave, meaning a wave whose wavelength repeats itself in 2 pi multiples, right, in the domain the wave is living in. So in the x-axis, right, the wave is just going to repeat itself, perfectly repeat itself. And if I take 2 waves that are completely actually in phase, and what I mean by that, they completely overlap at the same point, so the peak here at this position of x will completely coincide with the crest over here. And if clearly your intuition is correct, if I add these waves up together, right, I just basically get a resultant wave with exactly the same wavelength, but twice the amplitude. But I can do the reverse, right? I can actually disentangle this into 2 waves like that. So that's the idea of the superposition principle. I could do something else now that's also interesting. I could take the same exact wave with the same exact wavelength and basically shift this guy 180 degrees, okay, out of phase. And what I mean by that is literally where there's a peak now, there's a trough. And if I add those waves, what do you think is going to happen? Right? That's my definition of zero. You know, in quantum field theory, which is one of the things that I work on a lot, I tell my students, I said, particle annihilation is literally this picture. Okay, so, all right, so this is the basic idea. So this is nothing more than what we call constructive or destructive interference, right? Now, if I do the following thing, things get more interesting if I add waves up, more waves, more periodic waves, I end up getting much more complicated resultant waves. Now, what I just explained to you here is this notion of the Fourier transform, that I can take a signal, let's say, in the time domain, right? And it's very complex, but I can perform this transform, which I'll reveal in a second what that is. And what that will do is it will disentangle into a superposition, a linear sum, right, of simple periodic waves. So in other words, mathematically, right, if I'm presented this complicated function that's changing in time, complicated wave, right? If I know this thing and I sum over all frequencies, or think about it in the continuum as an integral, I can reconstruct, right? I can basically produce all the individual waves here, and I can do the reverse. If I take all of these different waves of different frequencies, that's f of omega, where omega is a frequency, and I perform this integral, I can reconstruct this function. So I can do the inverse. Well, this is very powerful because this is the mother language of much of physics, much of signal processing, much of computer science, okay, and much of mathematics, actually. All right? This is Fourier transform. But this is also at the heart of music. So let's actually demonstrate the Fourier transform. If I take something that's a column that can trap air, and this column can resonate, meaning that it will vibrate if I actually impinge vibrational energy into it, this thing will create wave patterns, okay? And the wave patterns that you will generate, the ones that it resonates best at, right? Meaning that there are natural frequencies that this thing likes to vibrate at that has to do with its geometry, right? Divisions of the length of this instrument will generate a spectrum, a range of frequencies. And I'm actually going to play some of this for you. I'm going to play, first of all, what we call the fundamental. This will be the lowest note on the instrument. In this case, it's B flat. So if I clip down all the holes, the wave is only allowed, there's no air is allowed to escape. And so I'm going to create a wave pattern that looks like that. And that has a vibration, all right? It has a frequency. And that frequency is a definite number, right? Now, this instrument is vibrating at other frequencies, it's just not as loud as the one that you're going to hear. And that's why I call this resonance. Because resonance is where most of the energy of my source is going into, is being absorbed into that vibrational mode. So let me now play that. All right, so that's my B flat. This is. What if I split the wave in half? So the wavelength now gets divided into half. What would I get? Any guesses? All right. You said an E. All right. So it's a consonant note, but you actually get an octave. You get high B flat. All right. What about if I split it in third? Or 2/3, the original.
Well, I would say you get it could be a major third or a minor third.
Okay, you actually get the perfect fifth.
Okay.
All right.
All right.
Like high over 4, like trigonometry here.
All right. So, yeah, let me play that. That's from 2001 Space Odyssey. Right? So the perfect fifth is actually the most consonant note aside from the octave. And in fact, if you treat the octave as an equivalence class, meaning it's identical, the next most important consonant note actually happens to be the integer, the ratio 2/3. All right? And if I get perfect fourth, then I get the perfect fourth. 1/4 is perfect fourth. That's
Okay.
That's a Miles Davis song called
Yeah,
fourth,
yes.
because it uses a fourth.
Yes.
Okay? So it's a very important device in jazz music.
I just like to say one thing in regard to you deal with music from a mathematical point, as opposed to, well, I'm a piano player myself, I'm jazz, but if you ask me about the mathematics of the sound, but I understand the concept.
Yeah. So yeah, let me make a very important disclosure. There are many approaches, all right, to music. Many approaches. The same way there are many rivers to the great ocean, right? I'm giving a perspective here because what I want to do is to highlight something in particular, which is that when I talk about Coltrane, right, I want to basically make the argument that Coltrane also was a mathematician. And that in jazz culture, even though, right, there's improvisation, right, the case I'm also going to make is that there's improvisation in mathematics. There's improvisation and illogical thinking in physics. The same way there's also mathematics in music. But it doesn't, music is its own thing, and many things can go into it, right? But that's kind of one of the things I want to highlight in this talk.
Okay.
All right? All right, so I'm not negating anything else about music and what music is. I'm just adding to the conversation. So, good. So this is, I just wanted to kind of show you that if you know your do, re, mi, fa, sol, la, ti, do, you've been doing the Fourier transform, okay? That's a basic point. Now, musical thinking in the sciences and in mathematics actually wasn't anything new. I realized that actually the journey I was embarked on, I thought I was like treading like new territory. The very birth of, so-called ancient science, okay? Pythagoras, who, spent about 18 years in Egypt, okay? Pythagoras came back from Egypt with this belief and this conviction of harmony of the spheres. That basically the order that they deduced about the universe at the time came from the fact that the planets were playing a perfect integer ratio in harmony. And that's led him to discover actually the musical scale. Then, fast forward 1,500 years, after many astronomers failed at trying to figure out motion and why planets were moving the way they were moving, and to explain things like retrograde motion of Mars, Kepler returned back to Pythagorean thinking. And what we see down here is that this is Kepler's own handwriting in trying to understand how the planets were going around, trying to figure out what type of motion was happening. Kepler actually wrote down musical notes. So here's how we approach the problem. He started to listen to Turkish and Arabic music, as well as polyphonic music from Europe. He started to listen to non-Western music and realized that the singing, that the tones could continuously vary. They didn't have to be individual discrete notes. And so when he started to use Pythagoras' idea that the planets were playing music, playing notes, he said there must be some divine force that is enjoying that music. And that divine force must be living at the center of the sun, where it's listening to this to the sound. And so he decided to write down those sounds. What he did was, he already had measurements of the velocities of the planets as they were closest to the sun, and the velocity furthest away. And just like we did with the division of a string, he took the ratios of those velocities, thinking of them as frequencies, and wrote down notes from those ratios. And these were the scales. And basically he used that and he generated the major and the minor scale. Okay? So if, it's a nice fun thing to research. But the basic point is that was the intermediate step that Kepler made to writing down his equations for the very first time. As you know, Kepler is known as the very first astrophysicist because he was the first to write down equations and to figure out equations that were correct. So this is Kepler's second law, right? Which basically says that if you look at the time a planet travels when it's closest to the sun, right? If you look at that time of transit, and if you look at the equal amount of time that a planet transits when it's furthest from the sun, it always will sweep out the same area. Okay? And that, basically, at the end of the day, is a fact of an elliptical orbit. All right? Now, it took Newton later on to realize that this was deeply connected to the conservation of angular momentum. But it was Kepler that wrote down the equations for that. But he got to it, right, by musical intuition. He didn't jump in there and say, oh, just write some equations down. He first developed the correct intuition, had a sense of what the geometry was from his genius, right? I mean, there was another leap that had to be made there. And then wrote down the famous equation. What is it? Is it the semi-major axis cube is proportional to the period square?
Yeah.
Okay. That's coming from Kepler's orbit intuition. So I decided that, hey, maybe I can have some fun myself. And so, physicists, you mathematicians have it easy. You know why? Because you guys, you guys can just do a calculation. One of my physics friends told me this. He goes, my mathematician friends told me, the guy was really a very powerful mathematician. He was a number theorist. So, remember the Ethiopian guy, Solomon, in the math department? Yeah. He was a brilliant number theorist that became a banker. Okay. So this guy once told me, he goes, you physicists, you guys go, you stumble across something and make a mess, and we come and clean it up. All right, that's pretty good. Okay. But here's my take on mathematicians. You guys don't need to have any, you could just do a calculation without knowing, like a physicist would look at an equation like, this thing means this. There's some ontology about the physical world with this differential equation. You guys can actually just blindly just crunch away and do a calculation and get new results without ever caring what it means. And you know it's true. And and we're kind of envious about that. I mean, physicists are kind of envious about that, right? Because we can't do that. We have to hinge on some kind of intuition to get to the next step. But I think that's what makes actually our ongoing collaboration over hundreds of years between physicists and mathematicians so amazing, right? That's how progress is made. So I decided, you know what? One of the things that we really struggle with as physicists, and I know Joao will not disagree with me, maybe he wants to because that's why he's sitting in the back of the room, is that we have a very hard time intuiting quantum mechanics. Like, we can literally, I mean, it's a first order linear differential equation. How much easier do you want this to be, right? The Schrodinger equation is right there. You can go ahead at it. But for some reason, intuiting, having an intuition for this thing is, I taught a graduate level quantum mechanics class a couple of years ago, and I remember the time I was in the blackboard, and I remember I stopped and I remarked to the student and said, I'm writing this stuff down, but I have no idea what I'm writing right now. And the students were like, why are we in this class? All right. So here's the thing. I decided maybe my music can help me, sort of get a different perspective on how I think about quantum mechanics. So I want to kind of share that with you right now. All right. So Richard Feynman reformulated quantum mechanics. And in fact, this is the more correct and the more modern way to think about quantum mechanics. And the reason why is the minute you take quantum physics and you go to the relativistic domain, you go to the domain where the speed of light becomes important, you're in the realm of a quantum theory of fields, all right? And not single particles, but of fields. And there, it is best described by using Feynman's reformulation of quantum mechanics. And I want to kind of like use music to kind of explain that to you. And I think it really helped me have a deeper understanding of quantum field theory. In the classical world, here we go. In the world of the very big, if I take this and I toss it in the audience, and I won't do that, all right? Because mathematicians are violent people, all right? One thing you can bet your bottoms dollars is that this thing will have a definite trajectory, right? And if you could trace out a line, right? It might be a parabola, but it's definitely going to be a definite and a unique trajectory, okay? And if you want to get fancy, a deterministic trajectory, okay? That's what happens. That's what this is supposed to represent. We have the classical particle at some initial time, and it moves to some final time. It's going to be, in this case, a straight line. In the quantum world, something very weird happens. All right? Something happens very weird. What happens in the quantum world, a single particle, according to Richard Feynman, will traverse every possible path. I just highlighted a few of them. Every possible path, okay, intermediate to the initial and the final point, already confusing, already like, my senses do not perceive that in the world of the very large, okay? How could one thing do that? First question. And also, it's only when you add up all these paths, you recover this path that you actually do see. Again, if you write down the equations, it makes complete sense, okay? In fact, you can formulate this in some ways as a Fourier transform, a special kind of Fourier transform, all right? Now,
so the classical picture is the sum of the quantum picture?
yes.
So
That's
it's
right.
the decomposition of
Yeah.
you decompose the deterministic path into a sum of
All of these probabilistic paths,
Sorry.
okay? Now, here's how Sonny Rollins helped me understand this. So Sonny Rollins, there was a famous article by a theorist and a critic. His name was Gunther Schuller, written in the 60s. And Gunther Schuller wrote a paper, kind of like a more academic music theory paper called Sonny Rollins and Thematic Improvisation. And the idea that Gunther Schuller, in his analysis of one of Sonny Rollins' solos, jazz solos, he analyzed the solo and he realized that kind of what Sonny Rollins was doing was similar to what happens in classical music, where you have a fugue, you have a theme, a motif. So Sonny Rollins would take a motif, and like throughout the song, he would manipulate and change the motif, right? So he wasn't the kind of guy that, right? So he would, that's what we call thematic improvisation. And what we're looking at here, I don't know if you can see it. Can you guys see down here? All right. This is actually a transcription of a solo that Sonny Rollins, an improvisation that Sonny Rollins is doing. And what I want you to realize is the following thing. I don't want you to pay any attention to the notes in between. Now you are, but I want you to pay attention to the beginning note and the end note. And I want you to now think about initial and final. So think about, this is time moving in this direction, right? And I want you to think of these notes as a beginning and a final note. And I want you to think about what's happening in between here as he's improvising. But actually what's really going on, right, is that Sonny Rollins is targeting. He basically knows the initial and the final notes ahead of time. And notice that the first note here is D, and the last one is G. Those notes are harmonically related, right? Right? They're related by perfect fifth. So whatever happens in between that actually will work. So at any given point in time, Sonny Rollins has many choices in between that he can make. He makes a choice, of course, but the next time there's another choice he makes. And I want you to think of those choices being considered as possible paths. All right, so the reason why this helped me was that I started to not think of a quantum particle, right, as a probabilistic sum, because I have no intuition for probability. But I started to think of the electron as an improviser. That when the electron goes from point A to point B, like a jazz soloist, it's improvising. Okay? Right. So that's my take on the pathonym.
Yeah.
So that's quantum mechanics, okay? Quantum particles improvise.
Yeah.
Now what's interesting there, improvisation is not random. Improvisation is informed by the harmonic structure, for example. And that is what we call a constraint. So you see, what happens is that the analogy, when you start, if you accept the analogy, then you start making comparisons. What you find is that this analogy making helps you ask questions that you never thought that you would ask before. And then it opens up a door for new discoveries. So in fact, what I was doing, and this device I was developing, by using music as a light to shine on things that I already understood in physics, it led me to new questions, right? So it became a kind of a research device. Now, don't get me wrong. I'm not trying to make this case that I'm like some music madman going around humming songs and doing quantum physics, okay? I'm not trying to say that. I'm just trying to say that every now and then, like, I'll have this kind of random thought. But it's kind of like, we all do that, by the way. If you knit, you better believe knitting is going to show up in your math, right? I'm not looking at you because I assume you knit. Okay. Maybe you do. All right. All right. Now, I want to say some things about my field of research, right? My field of research is the following picture. All right, this is a computer simulation, and it comes, what the simulation is doing, it's actually being used to compare to real data of superclusters of galaxies. All right, so just give a sense of scale now. I think what I want to do now is to take the light down. And I'm not afraid the light is going to go down too much. If that's okay.
It's okay.
Thanks. I think that's a little bit better. You guys cool with that?
Yeah.
You know, Murray, is that cool?
Yeah.
Okay. My friend Murray is this great filmmaker coming out from California. Give him some love. Okay, so, yeah. So what we're looking at here, right, you see this stuff. You're like, what is this? Let's zoom in, actually, to this little box here. And zooming in that little box, if I expand it, if I magnify it, I start seeing a little bit more patterns here. This is about 500 million light years, okay? Okay, remember, a light year is the amount of time, you know, the distance it takes light to travel in 1 year. That's on the order of, like, what, 10 trillion miles, Rob? Yeah, it's about 10 trillion miles, all right? That's 1 light year. This is 500 million light years. That's the distance you're talking about. And now if I zoom in this little area here, because you see that these networks of whatever they are, whatever that is, right? It seems to be clustering to certain nodes. It's like graphs, huh? Okay. If you now zoom in, that's 150 million light years. And then when you zoom into here, each dot is actually a galaxy. Remember, a galaxy is a collection of stars on the order of, 500 billion. Okay? So what we're looking at here is patterns of the large-scale structure of the universe. The galaxies are organizing themselves into a certain pattern. And the name of the game in cosmology, right, and Joao and I, we are theoretical cosmologists, is that what we're really doing is we want to understand the physics that led this to be in the course of 14 billion years or so. And the reason why we want to do that is because it's a way of showing us how short we are of our knowledge of physics. Because what we realize is that when we apply the laws of physics to understand this, 90% of physics is missing. So we use actually cosmology as a benchmark to actually understand how to advance fundamental physics, right? So in other words, we can just look at the sky to learn about, the laws of physics, okay? And I want to kind of tell you that, again, some of the tools for investigating this can come from the language that we developed earlier on, okay? And this is a picture, a rendition of the baby picture of the universe. This is when the universe, remember that there's a picture as the universe expanded, right, and cooled. There was a time in the past where it reached a temperature where basically electrons can no longer bind to anything, including hydrogen. And so at that time, the universe was very hot, a very hot, charged plasma of electrons interacting with protons and this quantum soup, okay? Not quite a quantum soup yet, but it was basically, and this is a baby picture, okay, of that. A Nobel Prize was given for this. This is called the cosmic microwave background radiation. And what Joao and I work on, definitely more Joao. Joao got famous for actually making fun of George Bush Jr. He discovered a particular feature of this, and he called it the axis of evil. I don't think Bush was happy when he did that. And he was president at the time. Okay. So these dots, so the idea is that what we're trying to understand is how did this plasma, before there were any stars, any galaxies, anything, how did this kind of chaotic soup, okay, hot soup, as the universe cooled, become stars and galaxies? What is the physics that did that? Right? Now, this looks like gobbledygook. This looks like there's no patterns there. And what I want to do is actually use music now to understand this. Okay? Now, what I want you to think about now as a good analogy, think of the surface of the ocean. And you're in the middle of the ocean, the surface, you have waves, right? Undulating up and down. And you have moments where a tiny wave will be high, and one will be lower relative to the other one. So one has more energy and the other one has an absence. Or, in fact, let's think about it this way. One wave has more pressure because it's compressed, and the other one is less compressed, it has less pressure. Okay? And these colors basically denote whether it has, if it's blue, I always forget this, Rob. If it's blue, it has less energy. And if it's red, it has more. Correct? It doesn't matter. Okay, now actually it has less. Yeah. Yeah. So what we're looking at here is a way of understanding this. What's really going on when we see red? It means that basically that light, okay? The blue region is a region that's hotter, and the region that's red is a region that's colder. And if you actually think about what that might be, will create a wave pattern, okay, where the pressure, okay, the pressure actually, you get a pressure wave. Let me ask you a question. What's an example of a pressure wave?
Sound.
Sound is a pressure wave. So these are actually sound waves that appear to be chaotic in the early universe. Okay, now let me show you what the data looks like. If you actually do the Fourier transform of that data, what I really mean by that is that Fourier transform, think of those waves, right, as a complicated wave. A whole set of complicated waves. And what you're going to do now is say, I want to figure out, I want to sum all the different waves of different sizes and plot which ones have the highest contribution, right? So I'm doing a linear superposition now of all these waves and seeing which one makes the biggest contribution to this very complicated wave I'm seeing in the sky. You literally do that, and you actually plot, okay, how loud the sound wave is on this x-axis versus the size. These are big waves in the sky, and these are tiny waves as you get to this thing. And guess what? This chaotic feature in this picture, right, looks very different than its Fourier transform. You see patterns in the Fourier transform, whereas you don't see patterns. And that's the important thing about the Fourier transform. So the question is, what is this thing? What does it tell us about these sound waves? And the way to understand that actually is to look at the Fourier spectrum of a musical instrument. Let's just look at that. Here's actually similar to what my soprano sax did. So guess what happens? When I play my soprano saxophone, I actually am producing a sound wave, and that sound wave is actually a little bit more complicated than we thought it was. It wasn't just one pure tone. Okay, so what you're looking at here, very similar to this data here, frequency versus loudness. When I play one note in my soprano, it basically, the loudest note will be the note that you hear. But what happens at the instrument, as it vibrates, it produces a spectrum of other frequencies that you do not hear as the individual note. You hear it as the signature sound of the instrument. What do I mean by that? If I played a clarinet and a soprano sax, one is made out of wood and the other one is made out of metal, right? And I play this exact same note, you're going to hear the same note. But you're going to say, that sounds like a clarinet and this sounds like a soprano. Why? Because these other vibrations are revealing information about the material and the shape of the instrument. Guess what this data tells us? These peaks gives us information about the size of the universe and the matter content. The reason why we can deduce that we have dark matter in the universe is by looking at basically, so the universe in a sense is functioning, the physics is clear to us now. It's functioning like a very simple instrument. So that's the physics, right? And that's how so if you look, starting from this will look like gobbledygook, it makes no sense. But you apply a little bit of intuition, right? Now, the thing that's spectacular here, the universe was very simple back then. And somehow, like a generative music piece, it got more and more complex. How am I doing with time?
Remember geometry from that, you will.
We should talk about that. So I have a question. How am I doing with time? Because
You can take as much time as you need. You're enjoying it.
I'm not going to put people to sleep. How are you guys doing out there?
Yeah.
Are you guys having a good time? Or? You good? Okay, good.
Enjoying it.
So I now want to talk about kind of a secret reason why I wrote my book. I kind of wrote my book to make, I wrote my book to kind of make a, more of like, I don't know, a social statement to you. Because as an African American person, you know, like I come from a culture, right? And oftentimes, even we ourselves like to, again, separate, you know, kind of what we do. Like I remember when I was in college, like, and I went to like a very, you know, a very white college. Okay, there were 4 brothers in my class. Okay, 4. And you know, the interesting thing that was going on there was like, you know, we would really separate our social lives. Like, you know, when it was time to go dancing, we go dancing. But nobody be talking physics, you know, whatever. And then when it was time to study, we studied. We very much separated those things. I wanted to make the statement actually that when you look at the development of jazz music, when you look actually at what was going on in the 30s and the 40s, when bebop jazz, especially bebop jazz, was being invented and created, if you actually look at what the musicians were doing at Minton's Playhouse and the conditions surrounding that, and I don't have time to go into that, you would find that was very similar to what physicists were doing and how they were interacting with each other, right? Let me give you an example. When Max Roach was on his drums at Minton Playhouse, these guys the musicians were actually playing for themselves. And they would experiment. They would actually experiment with like different things. And sometimes they would make mistakes. Like, so for example, one example is that was, you know, instead of doing the 4-kick, as in swing music, that they were actually, instead of they were playing the left, they were taking that to the ride.
You're right. The cymbal.
The cymbal.
Yeah. Okay.
And then what happened was Max Roach actually dropped the kick at the wrong time. And then I think Parker said, that sounds really good, keep that. They call that dropping bombs.
Yeah.
That became part now of the bebop language, and it was a mistake. Again, similar things happen in the development of quantum physics. Like certain mistakes, intuitive leaps were made, and it stuck. So the case that I wanted to make in my book, without actually saying it explicitly, but by providing examples, was that sort of like the intellectual contributions of jazz was the modes of that inquiry were very similar to what was going on in the development of modern physics, 20th century physics. And also, there were some intellectual equivalences and parallels. So in other words, I kind of want to make the statement that black folk, we don't have to try to be different to be physicists and mathematicians. It's kind of inherent in our culture. It's just expressed a little bit differently, but that's okay. Russian physicists, the way they do physics is a little bit different style than British physicists or than Portuguese. I don't know, you guys do physics? No, you don't do physics. You just rob people. So I want to kind of say a little bit that, that jazz and innovation parallels like developments in mathematical physics. There are these parallels that I found interesting. And as Abdus Salam said, one day he told Jim Gates, the great physicist, he flew Jim Gates out to Italy when he was a director of ICTP, had already won a Nobel Prize. And Jim was like, wow, I'm here with the great Salam. And Salam took him out to lunch and said, one day, when your people really do physics, it will look like jazz. So I now want to kind of end with my last little sort of piece. Okay. Can we learn new things about our universe? And I mean by universe, I also mean mathematical universe, okay? I'm being inclusive here. From music. So now I want to return back to Coltrane's thing. What is this diagram screaming at you and telling you? If you were to just decide to say something outlandish, what does this diagram show you?
It shows me that you the cycle fifths of going this way and counterclockwise the cycle forward.
Okay, you're being too technical there. I just
All
want
right, okay.
I want a mathematical idea coming out of
All
it.
right, okay.
I want a mathematical insight. The simplest thing that you see here.
Unicircle. Circle. I'm thinking unicircle.
Okay.
Group graph.
Yeah, the group
Okay.
graph,
You definitely see symmetry, right?
Yeah.
So you see basically, in fact, what this thing has is a 60-fold symmetry. That's why there's 60 lines here, okay? And then, of course, it has a 5-fold symmetry. It means that if I start doing transformations, this thing will look the same. So it has all these symmetry operations, and let me say the following thing. Coltrane read everything you can get about Einstein. My guess was that Coltrane knew about the function of the invariance principle in physics. So let me just say what Einstein really taught us, okay? Einstein did not like the word relativity. He thought about his theory as a theory of invariance. In other words, if I change something, if I change my physical system, all right, there are ways I can change things, and if I can change my velocity relative to somebody that's not moving as fast, so I can change my physical situation, right? What Einstein said is that the laws of physics should not care about that. So the laws of physics should be invariant with respect to changing. So the kind of math that you want to employ to do that is a principle of symmetry, right? You basically want to figure out what sorts of mathematical objects have where I can perform transformations, right? I can perform translations, maybe rotations, right? And then I can say, what object remains invariant here? And what Albert Einstein realized is that the 4-dimensional geometry, right, remains invariant. Very simple. Think about a circle, right? The radius remains invariant no matter how much I translate the angles, right? That defines the symmetry of a circle. Likewise, I can have a triangle. I can rotate this 3 times and it goes back to itself, right? So there's a 3-fold symmetry there. Okay, so on and so forth. Coltrane wanted to basically say to himself, what is the law of music that remains, what is the thing that remains invariant? Okay, if I, what is a geometry of music such that I get an invariant? And this was his guess. And the important thing here from Einstein is that there's a function that you're trying to, when I say function, I mean a physical function. So in the case of Einstein, that led him to understand why the speed of light doesn't change no matter how fast you're moving. Even if you're moving very close to the speed of light, it's still going to be the same speed of light that somebody who is not moving will see. The geometry that does that is what we call a 4-dimensional Minkowski space. Right? If you perform all those transformations, the speed of light in that geometry will remain the same. So the question Coltrane is asking is, what is a function of music if I perform transformations? Okay, so I made a guess, all right, that the thing that there's a structure that remains the same. And this is what it is. And what I want to do is now return and close my talk off with a very interesting demonstration. When I talked about the Fourier series, I talked about this Fourier series, right? I said that it's simply, it's math, right? I'm just taking integer multiples of a periodic wave, okay? And I am looking at basically the ones that are most consonant. Okay, so let's actually do that again. What I'm going to do now is I'm going to play, I'm going to exclude the octave and only play perfect fifths, right? Sequences of perfect fifths. Now let's assume that we are working in I'm living in a real line with that, okay? So I can reorder those things in ascending order. Any guess what you'll get? Any guess? What I'll get is a scale, okay? But it's a very peculiar scale. That's a pentatonic scale. So, you know, many music relativists and like musicologists will, you know, like to make a statement. Oh, you know, music is this arbitrary thing. Every culture has their own system. Well, the pentatonic scale is the one exception. This particular scale, right, is, to our knowledge, used by every culture that has music, has this scale. And it's musicologists think this to be a mystery. All right, actually, Bobby McFerrin has a video on this. If you Google Bobby McFerrin and pentatonic scale, penta because of 5. And this scale actually is very important because it is actually a very important device that jazz musicians use. We use the pentatonic scale to get through the 2-5-1 progression, for example. All right, because it contains the fifths and the 1, right? But it includes, the pentatonic scale has the major and the minor pentatonic built in it. If you know 1, you also have the minor. If I play the minor pentatonic scale and add 1 note to it, I get the following scale. It's the blues scale. So the blues scale is generated mathematically. The blues scale comes from Africa. Well, okay, arguably it's, you know, the gypsies brought it over, but it was prominent and very much developed, came over as the blues, and the blues scale is the basis of most popular American music, rock music, jazz music, right? You want to know how to play, you got to know the blues. Now, so I found it to be very peculiar, and that was why I think my guest Coltrane was that. He basically broke symmetry. What we have here is an object, which is a 5-fold symmetry. Again, this is just my conjecture, okay? It could be this complete garbage, okay? But this is the kind of game I play.
It's agreeable.
Huh?
It's agreeable.
Yeah. So you see this 5-fold thing that's generated here? This pentatonic, this thing? This would be perfectly symmetric because I can basically swap all these things and this 5-fold 5 times, and this object will remain invariant. All right? Or a better way of thinking about it is this house is actually, these transformations across this bisector will be invariant. Okay? Now here's what's interesting. If I separate all these by perfect fifths, right? It's symmetric up to going back from E to C, because that's a third apart, and so that object actually breaks the symmetry. I don't have much time to go into this idea of symmetric scales because there are 5 of them in the musical system, and their function actually is very similar to symmetry breaking in physics. That's where I'm going to go. All right? It literally functions identically to how symmetry breaking happens in physics. So this pentatonic scale is a first example of an important scale that arises out of symmetry but also breaks the symmetry. And I believe that Coltrane was hip to all of that, but that's just me. All right? So I'll just leave you with that. Thank you very much. Maybe answer some questions.
Yeah, we do have time for some questions here.
Oh, I really put people to sleep.
No, you here's the question I'm going to ask you. There's a possibility that mathematics and music is mathematics, but as far as going to John Coltrane, I think that the connotation you gave, I think that may be what he did, because you never know what a musician may do, like you call it invariant, from Charlie Parker, John Coltrane, Dexter Gordon, and I agree with that philosophy you gave, whether it's a conjecture or not. That's all I want to say.
Oh, thank you. I'm happy that you finally agree with me. Yes, sir.
The last thing you played sounded a lot like Dave Brubeck's Take 5. Is that a pentatonic scale?
Yes. I play that deliberately, actually.
Okay.
That's also just the tuning of a guitar, which you could tune in fifth as well, right?
Yes, right. Absolutely.
So let me maybe ask a question here about the symmetry. But why the number 60? Why are there 60 lines?
Very good question, actually. I think it has to do with physiology. I think that there's, and I could be wrong about this, but I think there's either something about the range of the instrument, because that's 5 times 12. So you have 12 notes in a so-called octave, right? So what he's really doing is extending the octaves of the notes. Normally, the geometry of the musical scale, the Western one, is Z12, right? The group Z12. And it's because you have 12 notes in a circle that basically go in a cycle. It's a cyclic group, Z12, and the transformations thereof. And that's why the perfect fifth actually is one of the generators are 5 separations, right, to close the group. Okay, so the basic point there is what Coltrane did was he worked in the group Z60. And remember that, and then Z5, tends to, the direct of the sum of Z5 and Z12 is Z60. So I think that, again, it's not arbitrary. So he was kind of looking for this invariant 5-fold symmetry in this thing. My guess is either something to do with the fact that the human ear can at most hear, these octaves best, okay? Or it's the fact that his instrument, that Coltrane was actually able to play 5 octaves, okay? But that was his constraint. That's the best I can do, because he really didn't talk to many people about this.
So here's a question for you. So
It was kind of investigative reporting.
So thanks, really nice talk. And I'm particularly struck by the notion of the universe as an instrument. And so 2 questions, kind of, what's the notion of the fundamental tone of that instrument? And then second, kind of the way in which you describe sort of the other overtones as kind of being peculiar to the geometry of that instrument. What's the way in which you've been thinking about that? Which is that would give us some sense of, as I'm sitting here thinking, I remember once listening to talk about the dark matter, and sort of my question was, well, what's the geometry of the dark matter? So in this, I'm thinking, what does the music say about what the geometry of this instrument called the universe is?
Good. So in fact, just the other day, Joao and I were talking about a similar thing, that in a lot of ways we are looking for that theory of the early universe, of something that transcends the Big Bang singularity, where it hums with that standard wave. Sound wave are special types of waves. They're standard waves, right? What I mean by that is that if I look at a wave, right, the nodes are always fixed. They're going to be these nodes, and the wave is not moving to the left or the right. It's just standing still, and the crests and the troughs are rapidly going up and down at a fixed point, right? We would like to understand if there's a way that the universe can actually persist to generate that while surviving something like the Big Bang, right? We're trying to look for that. We're trying to find that thing. We've measured the afterglow of that, which is in this data. In fact, the funny thing is that we call it in our field, this is called the first acoustic peak.
Wow.
All right? This is a particular frequency that is,
Dominant.
yes. We would like to understand where this thing really comes from and and if it came from something fundamental about the early universe, also how it persists, how it doesn't get washed out, right?
Would there be some natural reason why you'd be
But that's a great question, Albert.
at electromagnetics rather than gravitational waves or stuff like that, or just gravitational waves too inaccessible?
Well, the good news is that we know they're real, right?
Yes.
And there are one of my most well-known papers was actually a particular type of gravitational wave generated in the early universe, right? That in principle, if there are mechanisms to amplify it even more, okay, as the universe continues to expand, might be detectable. So the answer is yes, gravitational waves are very clean because they decouple, right, very quickly from ordinary matter, right, once they're generated and they propagate, right? So gravitational waves are actually astrophysically very clean things. So that's one of the new frontiers of astrophysics and cosmology. Now that we know they exist, they're going to be what's in the next big upgrade to gravitational wave physics? Is Lisa coming on board again? Okay. So we'll be seeing many more to come.
So I was thinking about the idea of sound being harmonic and noise is a distortion. In looking at your pentagonal design, how do you use the math to explain when you have a distorted situation?
Oh, that's a great...
I would imagine the Big Bang was kind of tumultuously distorted. How can you draw a correlation with that in your...
Well, there's a simple-minded way to do it, and that's a very good question, and thanks for reminding me to talk about this. The most democratic sound is actually noise, right? White noise. Basically, it's convoluted, right? It's a sum of equal amplitude of all frequencies, right? All right, that's white noise. And actually, the early universe, right? The period of during what we like to call inflation is a situation. Actually, it's very interesting where you have this white noise, and the universe is actually, I just had this thought the other day that what inflation is really acting as, if you really think about it, sort of post-inflation or the end of inflation is as a filter. Inflation generates this white noise and then filters out the ones that turns the volume down from the others. And what's left persistent are the ones, that the inflaton is coupling to the most. That's a thought, but we should return back to, thinking about that in a non-inflationary situation. I knew there was something I wanted to tell you, but your question reminded me that.
I'll buy you a book if that.
Okay, very good. You'll get 5% off.
Maybe let's take one last question.
And I want a really speculative, crazy one.
And I want one from one of the students.
Those are usually the hard ones.
I got one. So I see how you explain how using your music kind of influenced how you understand physics. Do you see it becoming? Do you see that happening more often, and how that would enhance what we know today, or how much we know today about what's going on?
That's a nice question. Actually, I wrote the book as I wrote my book because I wanted to understand things better. So it was an exercise to basically learn some things. These days, so the exercise was done. I wrote the book. I've given book talks, but I also want to make it, clear that, that there are months will go by, and I will not think about music and physics in that way. But every now and then, like, you know, I'll have like a curious thought, right? And that's kind of like, you know, it's more to do with having that intellectual freedom to let your mind wander and have those thoughts, all right? That's very important, you know? Like, discoveries are made often by trusting your subconscious to just be as irrational as it may be, and trust that the tools and the vocabulary that you've developed will find its place and help you morph into something else. And having conversations, engaging with your friends, and having soundboards is also a very important thing. And it'll make sure that you surround yourselves with friends that you can share your crazy ideas with. You know, one of my friends is back there, is a mathematician from the Graduate Center, you know, one of your cousin schools. And, you know, we were grad students, and we used to yell at each other at bars and things like that about, remember Han? Han is back there. You know, I mean, he's an applied mathematician, neuroscientist, and I used to ask him crazy questions about quantum mechanics in the brain, and he used to laugh at me, call me a buffoon, an idiot, all these things. But it was important to have that, and not feel like, you know, not feel judged. I used to call him an idiot too, right? So on that note, unless, yes, you got a question?
More of a suggestion. I'm inspired by what I'm hearing here. I never thought of music in that way. We live in a time when, unfortunately, our people are under pressure. I'm going to put it as mildly as I can. In particular, our black young men are under severe pressure. Just listening to you right now, I'm very inspired by what I hear. I'd like to see some kind of outreach from you or people in your sphere who are helping our young people to gravitate more towards the field of sciences, mathematics, and sciences. And I can see that what you're doing here will have serious impact if you were to take it to the high schools and middle schools. Maybe young people on you so that they will be able to understand. That's just my, it's very inspirational. It would help a lot.
Well, thanks for that, and you know, something that I know that, you know, we as a community, we're all on board with this, and I think that we should, you know, think constructively and strategically, because as you know, there are also forces out there that try to suppress this positive stuff, such that those areas in need it never gets to, even though there are efforts made to get that out there. So I think I totally agree with that, and it inspires me to hear that kind of awareness there. And I think that, you know, one of the things that, and that's why I'm very grateful that you so wisely decided to have a madman like me up here. You know, it could have been something to do with more traditional, you know, physics or math, but thank you.
Let's please thank our speaker. So I'm just going to give Dr. Alexander a plaque here on behalf of NAM. So quickly here it reads, NAM greatly appreciates your contributions to the scholarly activities of NAM and that of the larger mathematical community. So.
Oh, thank you, sir. I'll post it on Facebook.
So before we call it a day, let's see, Terrence, I'll let you come up if you have any announcements to make. I'll just make a couple of quick announcements. One, the shuttle will be here at 6:30. It is 5:53 now. Certainly we're going to go back to the Marriott, but if anyone needs to go anywhere, stay close to the Marriott. I think that will still be fine. Second, in the morning, the shuttle will be at the Marriott at 8 o'clock. We also will have breakfast here, bright and early at 8 o'clock, and I promise to get us back on schedule. The first talk will be promptly at 9 a.m. in the morning. So certainly have a great evening, and see you tomorrow.
So I just want to say thank you guys very much. I think we're at the end of the day. Thanks to everyone again. A special thanks to Stefan. And I think there might still be some food, so let's be sure that we don't leave the food hanging right there. Thank you guys very much. Wonderful day. Look forward to seeing you tomorrow morning at 8 o'clock. The slides are Idre, did you save the slides on the line?
I just have them in mind. Yeah,
yeah, I think that would be good. Kind of put the slides, your slides, as a link to the talk. That would probably be nice. Thank you.
Put the 60 resources for a lot of drafting.
Oh, yeah, I did. Yeah, do you have it? I'm just going to come right down. Okay. Oh, yeah. Oh, I understand.
Did you get with the fight? Oh, really? Yeah, you this. So someone was following the. What? You guys just have a fight.
Was it short off that spot?
Yeah. Where we were going out. What about 10 minutes?
I'll be right back. Yeah.